All right. So we're back looking at the wonderful world of FEMAP, and if you recall, last time we were looking at this problem, this beam here on the right, and we laid out our nodes and elements and what have you accordingly. One of the, I guess, different things about how we did this analysis is that we sort of directly, we sort of like hard-coded our mesh, if you will. We didn't create a geometry and then mesh it. Instead, we literally drew in the nodes, drew in the elements, and ignored that geometrical definition and just analyzed it accordingly. Now, I have a save file of that model, and I have it right here. So this is the model that we ran last time, and we noticed kind of a problem with the results. If you look at the deflection, that is not how a beam deflects, right? It's not what they look like, okay? Now, there's a couple other interesting issues with this analysis that we're going to be able to resolve today and clear up a little bit. But there's a couple things I want to show you all. First off, does everybody have this saved from last time? Okay. Well, I'll email this to you all maybe by the end of business or what have you, but we're going to redo it anyway, so it's not really going to matter. But a couple things I want to show you. So let me go back to an undeformed view. And this is something that anybody who does a beam analysis is going to want to see. I mean, what's one of the most fundamental set of tools that you use when you're designing beams? You have deflections, but there's also, I mean, what do you learn when you take statics and mechanics of materials? You got a beam, you learn how to draw these. Shear and moment diagrams, right? Is there a way to get FEMAP to plot the shear and moment diagram? The answer is absolutely. Okay. Now, let me show you how that works. Okay. So what you can do in FEMAP and the way FEMAP generally works on day one is it plots a contour. Remember that very first problem we did? We had the beam clamped on the side and we applied a load and we got that nice rainbow pretty contour or what have you. Well, what I will do is show you all how to do a moment diagram. And the way that we do that is we go to View and we go to Select. Okay, everybody see it's like F5, what have you. Now, if you look, probably what's clicked on yours is it just says Criteria or Contour here on the very right. What that does is it tells FEMAP what to plot when you say, okay, plot me a contour. Instead of plotting a contour or criteria, how about I plot a beam diagram? So I'll hit OK on beam diagram. And then I say, all right, well, what do I want? All right, if you go to right-click, or you can do it here up here in this toolbar or down here, see where it says Post Data? That's where it's actually picking what it is that I want to plot. I've got the deformed shape is based on the total translation. Instead, why don't I plot the contour based on, I don't know, the shear force at the ends or what have you? So maybe shear force 3018. Hit OK. Then when I turn on my contour, wait, did I not? Hold on, let me see something. View, select. Did I hit OK on that? Oh, nope. There we go. Must have hit cancel or something. Okay, it's not liking me right now. Give me a moment. Let me try that. Let's see. View, select, beam diagram. Hit OK. Oh, now, doesn't seem to like my little beam diagram selection. I don't know why. I did this in the office and everything worked great. Of course it did. Give me one moment. No pun intended. Select. Okay. Beam 1 and shear force. I don't understand why it's doing that because I just had it working a moment ago. Let me try something. Try opening it again. view, select, beam diagram, okay. Now, this is actually starting to bug me a little bit. Let me run the analysis again. View, select. There, okay, there it goes. I don't know what happened there. Maybe I just needed to run the analysis again. Okay, so what I did, just to recap, because I know I was probably clicking a bunch of buttons, y'all were like, what the heck is he doing? I was trying to get the visibility on the beam diagram. For some reason, FEMAP didn't like what I was doing, so I basically just reanalyzed it, sort of a trick for later. But if you notice, right here it's plotting, here on the bottom it says beam end A1, it says combined stress. Let me pick something that's a little more relevant, like a shear diagram. So if you go to, let's say, 3018 and hit OK. Oh, now, come on. Are you kidding me? What happened? Am I missing something here? Wow. I did, I swear. See, if I go to, let's say, maybe it was on that combined stress. View, select, beam diagram. I don't know what's going on there. It doesn't seem to like that one setting. I don't know. We'll fix it here on our next go through. Let me see something. I don't know. It doesn't seem to like that setting. I don't know why. I just did this in my office like a few minutes ago and it didn't enjoy that. Oh well, we'll fix it in our next setting. But the big thing that we need to resolve is that. The fact that the beam deflection isn't really amenable to what it is that we're doing. So what I'm going to do for this next method is I'm going to create a geometry, but I'm going to show you all some different meshing techniques that are going to make our lives a little easier. So what we're going to do is we're going to sort of start fresh, but we're going to analyze the problem a little differently. Okay? Now let's go back. Let me go ahead and not save changes. That's all that analysis I ran. Let's go back to the problem and just ensure that we remember what's going on. So one of the things that we're going to do that's a little different is how we handle this triangular load. Because before we were dealing with a single element, we just said, all right, let's just go from end to end and make it triangular. And we're going to see how that's really not going to work for what it is we're doing today. Because we're using multiple elements, that's going to make our lives a little more challenging. Now, to start off, let's just look at this geometry pretty rationally. So if we look at our beam, we say, all right, the total length of the structure from end to end is 96 feet, right? So 96 times 12, we said that was, what, 1152? I think that was what we used at the very end. Okay, I'm just going to draw a single line and mesh that, okay? Now, it's going to cause some differences in how we load and how we apply boundary conditions, but that work plane that we talked about earlier is going to help out quite a bit. So I'm going to start a new model. Excuse me. Bless you. Now, bless you. All right, let's do a couple things right off the bat to make our lives a little easier. So let's go to Model. Let's go to Material. Let's go ahead and create our material. We'll say that's made out of steel. And let's apply a Young's modulus of 29,000 and a Poisson's ratio of 0.3. So that should be pretty straightforward. Y'all okay with that by now? I'm going through that a little quickly, but I think we've had enough practice with that. Hit OK. Again, FEMAP says, give me more, give me more, give me more. You have to tell it, shut up. No, I'm done. All right. We'll say, all right. Next thing is, let's define a property. And I think what we used was a W12 by 40, I think it was, and we'll go off of memory. If our dimensions are off a little bit, that's no big deal for what we're doing. All right, it's made out of steel, and we have to change our property type. I think for this, I'm just going to use a beam. Just keep it simple. All right, is everybody with me with what I'm doing, or am I going too fast? Everybody good? Okay. So I'm going to create a beam, and then if you recall, what happened there? Oh, I hit the button here. I'm going to go down and create a shape. What? That's what I did. I hit the little thing on the ID. I'm going to go down and create a shape. Remember, we're going to do a wide flange section, right? And help me out. I think we had a height of, I think it was like 11.9, and our width was like 8.01, 8.01. What was it? It was like 0.515 for the top and bottom. Was anybody remembering these? Anybody write these down? Oh, that'll be right. I think that was 0.515, 0.515, and 0.295. I think that's what we used last time. Am I correct? Something about like that? So what I'm doing is I'm going in and I'm actually defining the cross-section that we use. We said we were going to use a W12 by 40 because its dimensions were and properties were close enough to what it is that we were doing. I'm going to give you all a moment to type that in and get everything ready. Is everybody good? Are you good, or y'all good? Need a minute? You want me to wait a minute, or are y'all good? All right, everybody good? Okay, so I'm going to hit OK and define that shape, and then when I've defined it, go ahead and hit Escape. So you should know you've done it correctly when it pops up again and it says ID2 in the top left corner, and then you know it's accepted that data. All right, sound good? Okay, all right. So now here's what I'm going to do for this geometry. I'm going to do things a little differently. Okay, we said the entire beam was what, 96 feet long, and 96 times 12, that's like 1152. So I'm going to go to Geometry, and I'm just going to create a single line to represent the entire structure from start to finish. All right, so we'll say maybe what I do, I should create a couple points. My first point, 0, 0, and my next one, what is it, like 1152? Y'all with me on that? All right, so 0, then 1152. So you should just have 2 points on the screen, and I'm going to go to Geometry, Curve, Line, then create a line based on points on the screen. I'm just going to go from here to here. Just create a single line to represent the entire structure. Yeah. Oh, okay. Hold on. Have you used this computer before? All right. That probably matters, actually. Let me see. Help. My goodness. There it goes. down the bottom. One more down. And then by points down here. Yep. Yep. So you all should have something on your screen looks something about like that, right? Are you good, or did you define your points?
Yes.
Okay, just one down. Right there. And then, where's your second? Whoa, what happened there? Oh, you're in isometric mode. That's why. All right, everybody good? Okay. Now, if you recall, in the last time we did this, we literally had like 5 or 6 elements for the entire beam. We're going to use a lot more this time. Okay. So what I'm going to do is I'm going to use an element every foot. Okay. Now there's a couple ways of doing this. If the beam is 96 long, I could say I want 96 elements, or I could say each element is 12 inches long. It doesn't matter. Okay. But in order to do that, I have to apply some mesh control. Remember that? So we go to mesh control, and then we can say size along a curve. Okay. So we'll say size along curve. What curve am I talking about? I'm talking about the only curve on the problem. So say okay, and then I've got a number of options. I could say number of elements. I could say element size. It doesn't matter. I'm just going to keep it simple. So number of elements. If I've got a 96-foot long beam, I'll say one every foot. I'll say 96 elements, and hit OK. So you notice. Now this mesh is a whole lot finer than what we did last time. Okay, so we'll hit escape because it's wanting more data. Then we have to mesh the geometry. Okay, so mesh geometry, we can only mesh the curve. That's all there is. What curve are we talking about? We're talking about that one. Now we're going to go through and mesh it based on a W12 by 40. We hit OK. Now what's it asking for? It's asking for the orientation vector. Do y'all remember what that is? There we go. What did you say again? Yeah, it's the Z direction, because remember, if we're talking about the I-beam looking like this, Z is pointing that way. So you could use +1 or -1. I don't think it really matters for our cross-section, but remember, if you had like different flange sizes, then it would matter. So I can do the base being 0, 0, 0, the tip being 0, 0, 1, or 0, 0, -1. And then hit OK. All right. So if I go into isometric mode and I say, all right, I want to see what the cross-section looks like. Remember, you've got that view style, the little gray cube up top. We say, all right, show me the thickness or the cross-section. You should have something that looks like that, right? Has everybody got that? Remember, it's right here. It should be a little like gray cube, and it should say thickness cross-section. You can turn that on and actually see the beam. Okay, yours is good, yours is good. Okay, you good? Whoa, what happened there? And you got another line here. What happened? I don't know what's going on with your model at all. So here, scoot over for a sec. Scoot over for a sec. I'm just going to fix a couple things. Give me one moment. Let's see. Here, I'm just going to start over, all right? I don't know what happened. So we're going to create 2 points, 0, then 1152. So you should have a point here and here. Go to geometry and create a line based on those points from here to here, and then that's it. Okay? Now we're going to go to material. Give me one moment, everybody. There's my material. Then go to model property. All right, we'll call it a W12 by 40. We'll change the material to steel. Now we turn it into a beam. And then say, all right, it's a W shape. Well, for our purposes, it all representative of a W12 by 40, but it really doesn't matter. I mean, if you were analyzing a different section, you'd have different data. So, okay. Okay. Then we'll go on mesh control, size along curve, do 96 elements, mesh the curve with, now your W12 by 40's there. Okay, and then make that 1. Now you should be able to orient that, and now you can see your beam. All right, does that make sense? All right. Okay, give me one moment. Okay, are you all good? You good? Oh. All right, that's 11.9. That is okay. All right. Are you good? Are you good? Okay, what's going on? Where are you at? What's because you got your notebook on the keyboard? All right, where are you at? All right, here. You want me to get you there? All right. What's going on with yours? Nowhere. You want me to get you caught up? All right, okay. All right. All right, so model, we'll create our material first. Hit OK. All right. Property. All right. All right. Okay. All right. Here. Let me scoot ahead. All right. That's the width. That's supposed to be 8. then this was 515. That was 515. And that's 295. Do you want me to catch you up, or are you good? What's that? Okay, all right. Are you okay with this? Okay, all right. Is everybody caught up? Or you good? Okay. Everybody else good?
So when I did the cross-section,
Well, you haven't meshed it though. All right, so go to Mesh Control, Size Along Curve. Got to select the curve. Hit OK. Then you need to tell it you want 96 elements. You have to hit OK. Okay, now see how it's divided it up? Now, okay, hit close. So now you've told FEMAP how many elements you want. Now you have to actually mesh it. So go to Mesh, Geometry, Mesh the curve, select that curve. And then you say, all right, change your property to the W12 by 40. Hit OK. Now here's where you put your orientation, and that second one needs to be 001. All right. Is everybody there? Okay. Okay, hold on. Are you good? Yeah. Okay. All right. Okay. Sorry, I guess I went a little quick on that. Okay. All right. All right. So is everybody here? Okay. All right. So I'm going to turn the thickness cross-section off because we don't need that. Now, what we've done is inherently created a model that is more accurate, okay, or should be more accurate. The problem is it might be a little more difficult to assign loads and boundary conditions, okay? So one thing I'm going to do is I'm going to go into that top view where I'm just looking in X and Y. And do you remember me talking about that thing called a work plane? Do you ever remember me mentioning that, where you drop down here, where you can turn on that cross-section, the thickness of the cross-section, see where it says work plane? Y'all see that? Turn that on, and you should get an image that looks something about like that, right? So what this is this is kind of a coordinate system for us, okay? And this coordinate system will help us identify our the locations of our loads and our boundary conditions and all that stuff a little easier, okay? Now, help me out. We have a boundary condition at x equals 0, at x equals 24 feet, which is what, 288 inches, x equals 48, x equals 72, and x equals 96. Am I correct on that? I mean, you all have the image in front of you, right? So this is 1152. Help me out. You all should have calculators, right? What's 48 times 12, and what's 72 times 12? 576. And this one's 864. Okay. Now, if you recall, if we go back to the beam image, the ones at the ends are fixed, and then these are pinned, or rollers, but it really doesn't matter. We'll just keep it simple and say they're pinned. Sound good? All right. So here's what I'm going to do. I'm going to go and I'm going to start to apply boundary conditions. So I go to Model, Constraint, and then in this case I'm just going to do Nodal and apply to the nodes. All right. So just hit OK on that. What nodes do I need to select for a fixed boundary condition? The one over here and the one all the way over here, right? So click this one and click this one. All right. Are y'all okay with that? All right. Hit OK, and just keep it simple. We'll say it's fixed. Do you all see that? Right here. All right. Sound good? Hit OK. And now it looks a little different since we're looking in the nodal perspective. The last time when we were applying boundary conditions to the geometry, that little F popped up. It said fixed. since we're looking in the nodal point of view, see how it says 1, 2, 3, 4, 5, 6? Now, that just means it's all three translations and all three rotations. Now, we've got pinned boundary conditions to apply. Here's where this work plane comes into play. Where did we say? Here, here, and here, right? Now, how do you determine where 288 is, 576 is, and what have you? The work plane. Now, let me show you a couple things, all right? Your mouse wheel zooms in, right? But if you take your mouse and try and like drag, well, first off, it'll either select a node or it won't do what you want to do. So watch this. Do you see these little arrows up here, the blue ones, like right there? You see those? Those will actually pan the image left and right. So if I go back to trying drawing those constraints, model, constraint, nodal, and then I use this, see how it's actually moving the image to the left and right? That'll help you navigate which ones you need to select. Now, we need 288, 576, and 864. So 288, okay? What do you think? Is that, what, that one right there? That one right here? Because see, this is 250. That's 300. So that's probably that one right there, isn't it? That's what this stuff's for. That's what that work plane's for. Okay, so there's that one. All right, what's the next one? 576? Probably that one, right? That's 575 if you split these two, right? Make sense? Then 864, probably that one right there. Are y'all okay with this? Am I going too fast? Any questions? All right. Hit OK. And for simplicity, we'll just say these are pinned. Hit OK. If you want, hit Control A to zoom, everything into place. But really, you should have something that looks like this. Yes. Well, you just hit that one and hit OK. Well, yeah, but those are fixed. Well, no, you do them sequentially. Like, have you applied it? Have you hit OK to this at all? No. Oh, well, then just hit fixed, hit OK, and then now do the next ones. Remember how FEMAP works? It's like give me more, give me more. So you can go ahead and just right here. That's what these are. Yeah, like the ones that it's like every quarter point. All right, are you good? Well, here, hold on, close up. It's just right here. Whoa, you got a lot of stuff popped up. It's just right there. Let me see. That one. Whoa. Yep, that one. And then what's 576? So that one. That's it. And then 864. So that one. That pinned. Yep. All right. Does anybody need any help? Okay, what's up? Huh? Right here. That's what those are for. Yes. Do you need help? Change what? how about putting it on top view? And then why don't we turn that off to where you can actually see this. Are you all good? You good?
Do you know what three of those were in the middle?
Right here.
I'm trying to read the notes. Okay.
The 288,570, that's what this is for. How are you doing? Do you want me to catch you up? Okay, why don't you scoot on over? All right, give me one moment. Give me one moment. Whoops. Forgot to hit OK. Okay. Sorry about that. Is everybody caught up? Like, is everybody with me? All right. I feel like there's some things we might have forgotten. Is everybody good? Okay. All right. Okay. So let's go back and make sure that we're all clear on what we're doing and why we're doing it. Okay. So what we've done is we've created a beam structure. We've fixed this end, and we've pinned it here, here, and here. Now we've created the material, we've created the beam section, and we've applied it to the structure, right? So what's the one thing we have left to do? Load it. We have to load it. Okay, all right. So let's deal with the simple ones first, okay? The simple ones being the concentrated forces, the point loads and the moments, okay? Now, a couple things. If this is x equals 0, where does this occur? This is x equals 16 feet, and 16 times 12 is? This is where your units, and you have to maintain a consistent unit system. 184? I was going to say, that's 192, right? Okay, now what about this one? This one here on the right. Okay, so that's 24, 12, that's 36. 36 times 12, 432? Okay, all right. So what I'm going to do is I'm going to go into the model and I'm going to apply concentrated forces here and here, my 40 kips. So we'll go to load, or model, load, nodal. I actually apply it to the nodes. And we'll say, all right. I just hit OK on that. And then, let's see. So 192, that's probably about right here, isn't it? That's 192. And then, let's see, 432. Let's see, that's 425, 432, that's right there. Hit OK, and then, okay, so remember, we are applying a force 40 kips downward, so what do? X, Y, or Z? Y, and what value? Minus 40. There we go. All right, there we go. Those resounding answers, that's what I like. Minus 40. Hit OK. Does that look right? Looks right. Okay, is everybody caught up with me? Okay, what's next? What other concentrated force am I missing? The moment right here. Okay, it's a moment in the Z direction, right? And it's negative, right? So what we'll do is we'll do the same thing. Model, load, a nodal load. Just because it's a moment doesn't mean it's not a nodal, effect. So we'll apply it to that one right here, the same one that one's at. Say, all right. And we go here on the right, or on the left, sorry, on the left, and we say, all right, it's a moment. And it's in the Z direction, and it's minus 75 times 12, or minus 900, right? Hit OK. Let me isometric that. Is that correct? All right, did I go too fast? Does anybody need any help? Everybody good?
I did not follow the last step.
What part? What?
After pointing on the loads.
After what? I couldn't hear the last part.
The one which we pointed out the Z direction.
Well, I just hit OK. What?
After pointing down the loads in 40 kips,
Yeah.
after that, this step I did not follow.
Well, I just redid it. I did a nodal load at the load at that location.
Okay.
Yeah. But then over here, I've got to turn it into a moment.
Okay.
And then it's on the Z direction. Yes. Okay. All right. Let's say you screw up. That's okay. It happens all the time. You go onto your model tree here on the left. See where it says model. Then you go to loads. Drop down until you find that last one that you created. You should see load definitions. Go to that moment one and just delete it. Just right click and hit delete. Okay, is everybody with me on this? Do y'all need, raise your hand if you need help. I won't know until you tell me. You good? Good? Good in the back? Okay. All right, what's up? Okay, you didn't put negative.
How can you know this is at 430?
Okay, again, that's what the work plane's for. That's what the scale's for. Now you tell me, is that one on 432? That's 400. That's 450. So that center tick, that's 425. Is that the right one? Yeah. So you see what I mean? We'll get to that here in a second. Look, hold on. First off, okay, a couple things. First off, we do know it's exact because we said we wanted an element every 12 inches. So we know that's the right point. You see what I mean? It's an even discretization. My point that I was making, though, is that that's on the wrong one. Okay, again, you go over here on the model tree, go to model, then your loads, and keep dropping down, and you'll see where you see what I mean? Just delete them and start over. What symbology?
Wrong at all. Here's the
Huh?
two figures. Figure 900. Ours is like
Let me. I don't think so. No. Is it in the right direction?
negative.
Did you do it on a point or on a node? I don't know that it really matters. It's the first time I've noticed that. It shouldn't matter. It shouldn't matter. So, is everybody good? Okay. All right. Okay. All right. Let's try and get this one done as quickly as we can, because I know we've only got like a few minutes. So, all right. So everybody watch with me, okay? Everybody watch up here. Okay. Everybody watch up here. Okay. All right. So the next thing we're going to do is we're going to do this distributed load, okay? So we have to place that distributed load from x equals 0 to x equals 192, right? So let me show you what we're going to do, okay? We're going to go and create an elemental load, all right? So let me get this back in that top view so that I can see what's going on, all right? Now, that load needs to be placed all in here, right? So let me zoom in a little bit. Let me zoom in, and then let's pan that over to where I'm looking at my region of interest, okay? So I'm going from here to here. Are you all clear with how I'm panning? I'm using those arrow keys up there. Sound good? Sound good? Okay, all right. Now, is this going to be a nodal load or an elemental load? Elemental, all right. So we go to model, load, we go to elemental, okay? All right. Now, before we do anything, watch me for a second, okay? Now, if you notice, look what I'm doing. I'm having to like click this one, and click this one, click this one. It gets kind of old, right? If you notice here, this dialog box is all about selecting elements. It's like, which elements do you select? See where it says method? Now watch what I'm going to do. I'm going to go to method, and then, well, or pick. Sorry, I meant pick. Sorry. Pick, and then I'm going to pick box. Okay, do y'all see that? Then watch what I do. Did y'all see that? Sorry about that, I meant pick. Okay. Y'all able to do that? Right here where it says pick, you can drag a box. All right. Sound good? Hit OK. Now, we'll do a distributed load. Okay? Now, we have to place the load at each end. All right? So it's what? -2 kips per foot. So take that -2 and divide it by what? 12. There we go. Okay. Hit OK. Then what direction do we place that in? Well, negative, yeah, but what direction? Y. So global Y, right? Just do it for the whole coordinate system. Hit OK. And you should get something that looks like that. All right, let's see. Looking good. Looking good. How's yours? Okay. Where's your boundary conditions? No. Did you do constraints? But they're not there. Where are they? You don't have any constraints on here at all. But we'll work on yours in a little bit, all right? Oh, you probably still have your, where'd your view toolbar go? Oh, make it solid, and then turn your cross section off. Okay, all right. You go here, you distributed, and edit it. Okay, that should be 24. You said 2 divided by 12. It's 2 times, or yeah, you did 2 times 12. It should be 2 divided, and it's got to be negative. Okay, what do you need to do? All right. Okay, where are you at? I'm not sure. Wait. You're on create loads on nodes. But we'll hit yours back up here in a little bit, all right? Okay. Okay. Y'all good? Y'all good? Y'all good? Okay, all right. Okay. Do you all have something that looks like this? Okay. What's left? What's our last 2 loads that are left? The triangular loads, right? Okay. For the interest of time, we're only going to do one of them because the time, this was taking a little longer than I expected. But we're only going to do one of them. Now, we're going to do this a little differently, okay? So everybody pay attention up here for a sec. So I'm going to show you a method for doing this called data surfacing. And the benefit of using something like a data surface is that you can do a fairly complicated analyses or fairly complicated load patterns really, really easily, okay? And it all goes back to something very simple. It all goes back to graphing, okay? Now, help me out with something, okay? Actually, I'll just do it here on the screen, okay? So here's my beam, right? Okay? Now, for the purposes of what we're going to do, I'm only going to do the one here on the left. So I want to look at these 2 points from here to here, okay? So help me out. If I indicate this point right there, what are the coordinates of that point? Well, keep in mind, or help me out. Whoa. That could have been bad. Say that again? There we go. 576, 0, 0. Do you all understand that? Because this right here, that's the x-axis. That's the y-axis. The z-axis is outside of the screen. What are the coordinates of this point? 864, 0, 0. Okay? So I've got these 2 points in space, okay? And now I've got magnitudes associated with them. What is the load magnitude on the left point? 0. What's the load magnitude right here? 3, or 3 by 12, right? Everybody okay with that? All right. So here's what we're going to do, okay? Let's go back to FEMAP. All right. So we're going to go to Model, Load, and we're going to create an elemental force, okay? All right? Now, we need to pick all of the elements between this support and between that support, right? Make sense? All right, so I'm going to select, pick based on this box, everything there. Does that make sense? So I've selected all the elements between support A and support B. And remember, I just did that based off this pick box right here. Sound good? Okay, all right. So, how do I do that in this box? Okay. Well, if you notice, look right here. We are placing a distributed load, but see how, okay, we're putting on the element, but see where it says method, bless you. We have constant, variable, but then we have data surface. Let's look at data surface. Okay. I'm going to create a data surface that represents this load, and I'm going to use it to apply the load to the section. Okay. Now, if you notice, it said, see where it says 0 and it says none? That's because I haven't defined any data surfaces at all. So if you notice this little box here on the right, it gives me a number of options. It says along coordinates, between coordinates, output map, all, you know, the math fanatics can get kind of really fancy with this. I'm going to create a data surface between coordinates. Okay? All right? And if you note, there's a number of different ways we can do that. We're just going to do a 2-point coordinate to keep this simple. So watch what I'm going to do. I've got coordinates and values. Okay, so my first coordinate is 576, 0, 0. Now, help me out. What's the magnitude at that coordinate? 0. Okay, the next one. Oh. The next one, what's the next coordinate going to be? 864, 0, 0, right? What's the magnitude at that coordinate? Negative 3 over 12. Make sense? Hit OK. So what we've done is we've created this data surface. Now, here's the kicker, okay? What this is asking for right now is it's asking for how much load to place on each element. And what I want FEMAP to do is I want it to use that data surface I just created to load every one of them. And since I already incorporated all of my magnitudes, what I'm going to do is see where it says load at end A and load at end B. I'm going to change them both to the data surface, and I'm just going to use a value of 1. So to give you kind of an idea, see how it's like from 0 to 3 kips per foot? If I did 2, it would be 0 to 6 kips per foot. Or if I did 10, it'd be 0 to 30 kips per foot. So I'll just use 1. So basically it's taking that data surface and multiplying it by 1. Let's just keep it simple. Now, we hit OK. We got to indicate a direction. What direction? Global Y. And it looks like a mess, right? This mess that popped up. I want to zoom into it. All right? Now, if you take a little bit of time and actually read what you see here on these loads, you'll see that they all make a lot of sense, because look what's happening. This very first element is loaded from 0 to like what? 0.0142, right? The next element is 0.0142 all the way to this. Third element from this 0.02 all the way to this. See how, while graphically it looks a little strange, see how numerically it's actually following that linear trend the way it's supposed to? And if you zoom out, what is the last magnitude? The one all the way over here. It's exactly what it should be, right? 0.25, 3 kips per foot, or 0.25 kips per inch. Does that make sense? So it's not applying a triangular load to the model. What you're doing is you're using this data surface to figure out, okay, how much load needs to go on each element to represent that. Make sense? Okay, all right. So, all right, everybody good? Okay, so now what we can do is we can go ahead and analyze this beam. So let me turn off, let's turn off that work plane. We don't need that anymore. And let's go ahead and analyze this. So we go to Model, Analysis, create a new analysis set, just hit OK, and run it by hitting Analyze up top. Okay. You'll know it's done because it should say cleaning of output set 1 is complete. Everybody got that? What happened? What's going on? Right. Just go to model, analysis, and then create a new analysis. Just hit OK and analyze. Okay, where are we at? Oh, yours is good. What happened to yours? I don't know. We'll have to look at it. All right. What's that? We'll look at it later. We'll look at it here in a little bit, all right? Okay. The big thing I wanted to point out is this, okay? Let's sort of keep our eyes on the prize because I feel like we're all getting lost in some of the minutia of these buttons and clicks, okay? The last time that we ran this model, remember how our deflection was just jagged and pointy. It didn't represent what beams truly are, okay? Now, if I go to visibility and I turn off, these loads and these constraints to kind of, reduce the clutter a little bit, and I actually look at the deflected shape, now there's the model before and after. You tell me, does that look like it makes a little more sense? You bet. That's what a beam looks like when it's deflected, right? Notice how it crosses 0 here, here, and here. Why does it cross 0 at those places? Say it again? It's where, well, it's not, no. Why, this is the deflection. Why is it 0 here, here, and here? That's where the supports are, okay? Now, here's another thing, and I think it's easier to see right here. All right, let me zoom in a little bit, and let me pan it. What is happening right here? The deflection's going to 0, but what else is going to 0? Well, what is its slope right here? What's the slope right there? If you have a curve and its slope is, it has a flat slope, what is the slope? 0. My point is this point, like if we look right here, its deflection is 0, but it's definitely rotated quite a bit. Is this rotated? No. What do we have there? We have a fixed support, right? Make sense? All right. Now, I hope this works, or I'm going to be kind of ticked off if this little FEMAP tries to get upset with me. All right. Let me go back and view everything. Now, what I'm going to do, let's see if this works. I'm going to go to View. I'm going to go to Select. And then I'm going to have it spit out beam diagrams. Then, based on what data? And we'll do it based on, let's say, moment. Hit OK. Hit OK. Are you kidding me? That's going to bug me. Criteria. I don't get why that is not working, because I was doing that in my office and it worked fine. I'm going to have to investigate that. That's actually starting to bug me. I don't know why. Because I had shear and moment diagrams popping up in my office, and they look good. I don't know. To be continued, right? I'll figure it out next time. Okay. In the meantime, let's just be clear. So on Tuesday, I'm not lecturing at all, okay? I'm coming in, and you all are working on this, okay? Does everybody have a copy of it? Okay, you're more than happy. Go ahead and start working on it now, but I'll be here Tuesday. I'll come in and you all work on this. Is everybody clear? All right, sound good? All right, that's all I got for you all today. You all have a good weekend, and I will see you all on Tuesday.